Hello there, and welcome to The Sleepy Astronaut, where cosmic mysteries meet gentle curiosity and the universe unfolds its secrets under starlit skies. Tonight's peaceful journey takes us beyond our earthly home to encounter one of the most extraordinary visitors our solar system has ever received. A wanderer from the depths of interstellar space that has captured the attention of astronomers worldwide and sparked questions that reach to the very heart of how planetary systems form and evolve. Before we drift into this cosmic tale, I'd love to know where in the world you're listening from tonight. And when you look up at the sky, what do you wonder about fitting? Isn't it that as we explore the nature of this mysterious traveller, you too are travelling through space aboard our pale blue dot spinning gently through the darkness? If this voyage of discovery brings you comfort or curiosity, I'd be grateful if you gave the video a like and perhaps subscribed it. Helps this little corner of cosmic contemplation reach other stargazers who might need a moment of wonder before sleep. Now, I do hope this isn't so fascinating that it keeps you alert, but if it does well, at least you'll drift off knowing something remarkable about our place in the vast galactic neighbourhood. So settle in, let your thoughts slow like distant starlight, and let's begin. Because somewhere between the familiar dance of planets and the alien depths of interstellar space lies the story of a visitor that has changed how we see our cosmic home. Space has a way of delivering the unexpected, doesn't it? One moment astronomers are tracking the predictable orbits of familiar comets and asteroids. The next moment they're scrambling to understand something that shouldn't exist in our neighbourhood at all. Something that travelled for millions, perhaps billions of years through the cold emptiness between stars, only to arrive at our doorstep like a message in a bottle, cast into an ocean of unimaginable vastness. On July 1st, 2025, that's exactly what happened when a survey telescope in Chile spotted something unusual moving against the background of stars. It wasn't behaving like the objects we know it was moving too fast, taking a path that suggested it came from somewhere else entirely. And as observations poured in from telescopes around the world, one thing became crystal clear. This wasn't just another space rock from our solar system. This was something far more extraordinary. The object received the designation 3. I-Atlas, a name that tells its own story. The 3I marking it as only the third confirmed interstellar object ever discovered by humanity. The Atlas, honouring the survey system that first spotted it, but names and numbers barely capture the profound implications of what astronomers were seeing. This was a visitor from another star system, a piece of cosmic archaeology that had drifted through the galaxy, carrying secrets about worlds and processes completely alien to our experience. Imagine for a moment the journey. This object undertook long before our sun formed, before Earth took its first breath, before life stirred in primordial oceans. This wanderer was already ancient, already travelling through a galaxy that looked very different from the one we see today. It may have been ejected from its home system during the chaotic early days of planetary formation, when gravitational interactions flung debris in all directions, some settling into stable orbits. Others, like our visitor, cast into the eternal darkness between stars. The discovery process itself reads like a detective story, scattered across telescopes and time zones, as astronomers pieced together observations that painted an increasingly remarkable picture. The object had actually been visible for weeks before its official discovery, hidden in plain sight against the dense star fields of our galaxy's centre, where countless suns create a tapestry so rich that even something extraordinary can remain unnoticed until the right eyes look at the right moment with the right tools. What made this detection even more remarkable was the collaborative effort it required. Within hours of the initial spotting, observatories around the world were turning their instruments toward this cosmic visitor, each adding pieces to a puzzle that revealed something unprecedented. Amateur astronomers joined the effort, their dedication and skill proving once again that the universe belongs to anyone curious enough to look up and wonder what they might find. By the time the object received its official designation, Astronomers had collected observations from dozens of facilities worldwide, creating the most comprehensive picture yet of an interstellar visitor's properties and behavior. And what they found challenged expectations in ways that continue to ripple through the scientific community. Like the wake of a ship crossing still water, the physical characteristics of 3I Atlas began to emerge from the data, like a photograph developing in slow motion, and what astronomers saw defied easy categorization. This wasn't simply a larger version of the previous interstellar visitors. It was something qualitatively different, something that suggested our understanding of what gets ejected from other star systems needed serious revision. The size estimates alone were staggering. Early observations suggested a nucleus, somewhere between 440 meters and 5.6 kilometers in diameter. But as more sophisticated instruments focused on the object, and as researchers refined their calculations, the numbers grew larger and more puzzling. Some estimates placed the mass at over 33 billion tons, making it not just the largest of the 3 known interstellar objects, but so much larger that it represented what scientists carefully term an anomaly of several orders of magnitude. Think about that for a moment. When scientists say something is anomalous by orders of magnitude, they're being politely understated. They're saying that according to what we thought we knew about interstellar objects, this thing shouldn't exist, or at least it shouldn't have been the third one we found. It's like expecting to catch minnows and pulling up a whale. The velocity measurements added another layer of mystery to an already puzzling visitor. When 3I-ATLAS was first spotted, it was traveling at roughly 137,000 miles per hour. But as it continued its approach toward the inner solar system, that speed increased, reaching approximately 245,000 kilometers per hour, making it one of the fastest objects ever recorded in our cosmic neighborhood. These aren't the gentle orbital speeds of familiar comets and asteroids. These are the velocities of something that has spent eons in the deep cold between stars, building up momentum across distances that stretch the imagination. The trajectory calculations confirmed what the speed had already suggested. This object came from elsewhere entirely. Its path through space showed the telltale signs of an interstellar origin, with an eccentricity that marked it as unbound to our sun's gravitational embrace. It was passing through our solar system like a tourist, stopping briefly to see the sights before continuing on a journey that would take it back into the galactic depths from which it came. But perhaps most intriguingly of all was the direction from which 3I-ATLAS approached our solar system. Unlike the previous interstellar visitors that seemed to originate from the thin disk of our galaxy, where most stars, including our sun, reside, this newcomer appeared to come from the direction of Sagittarius, from the thick disk region surrounding our galaxy's central bulge. This suggested a different origin story, perhaps a more ancient one, involving stellar populations and processes that formed when our galaxy was younger and more turbulent. The implications of this directional information ripple outward like waves in a pond. If 3I Atlas truly originated from the galaxy's thick disk region, it might represent material from an earlier epoch of galactic evolution, when star formation proceeded differently, when the chemical composition of stellar nurseries differed from what we see today. In that case, this visitor wouldn't just be carrying information about another star system. It would be carrying information about another era of cosmic history. As observations continued throughout the summer of 2025, another remarkable characteristic emerged from the data. 3I Atlas wasn't behaving like the inert chunk of rock and ice that many had expected. Instead, it was active, displaying the kind of behavior typically associated with comets as they approach the sun and begin to heat up. But this activity began much earlier and much farther from the sun than anyone had anticipated. When most comets begin their spectacular displays of outgassing and coma formation, they're typically much closer to our sun's warming embrace. But 3I Atlas started showing signs of activity while still beyond Jupiter's orbit. a distance where the solar radiation should barely tickle the surface of an icy nucleus. This early awakening suggested something unusual about the composition or structure of this interstellar wanderer, something that made it more sensitive to the sun's distant touch than the comets born in our own cosmic backyard. The early activity manifested as a subtle glow, a brightening that caught the attention of automated surveys designed to spot changes in the night sky. It wasn't the dramatic tail-streaming display that makes headlines, but rather a gentle increase in brightness that spoke of gases and dust beginning to escape from a warming surface. Even at that tremendous distance, the sun's influence was beginning to coax this ancient traveler into revealing some of its secrets. What made this early activity even more puzzling was its apparent randomness. Or perhaps we simply didn't understand the pattern. Yet observations from NASA's Transiting Exoplanet Survey satellite suggested that the brightening might have begun as early as May 2025, when the object was still roughly 6.5 astronomical units from the Sun, that's beyond the orbit of Jupiter, where our solar system's familiar comets remain frozen and dormant, waiting for their much closer approach to begin their own spectacular transformations. As summer progressed and more telescopes focused their attention on this cosmic visitor, another mystery emerged, one that seemed almost playful in its defiance of expectations. 3. Atlas began changing colors, like some sort of celestial chameleon. Initially, the object appeared reddish, a coloration that astronomers associate with certain types of asteroids and organic compounds that have been weathered by eons of cosmic radiation. This reddish hue made sense for something that had spent millions or billions of years drifting through the cold emptiness between stars, accumulating a patina of space weathering. But then something remarkable happened. Amateur astrophotographers capturing images of the object in September noticed that it had transformed from its earlier reddish appearance to a distinctly green glow with hints of blue. The change was so dramatic that it appeared to have switched colors like a cosmic traffic light, shifting from the warm red of caution to the cool green of go, as if the universe itself was giving permission for some new phase of the visitor's journey. This color transformation wasn't just aesthetically intriguing. It provided crucial clues about the chemical processes occurring. As 3I Atlas warmed up the green glow, typically results from diatomic carbon molecules in a comet's coma, absorbing ultraviolet light from the sun and re-emitting it at specific wavelengths that our eyes and instruments perceive as green. It's a signature of active outgassing of carbon-bearing compounds being liberated from the nucleus as ancient ices sublimate directly from solid to gas in the vacuum of space. The blue tinge added another layer to the chemical story, suggesting the presence of other molecular species, perhaps carbon monoxide, or other simple compounds that had been locked away in the interstellar deep freeze for geological ages. These weren't just pretty colors. They were the spectral fingerprints of an alien chemistry, the atmospheric signature of processes that began in another star system under conditions we can barely imagine. As autumn approached and 3I, Atlas continued its journey toward its closest approach to our Sun. The most sophisticated space telescopes humanity has ever built began turning their attention to this cosmic visitor. The James Webb Space Telescope, with its unprecedented infrared vision, started peering through the growing coma to analyze the chemical composition of the gases being released, and what it found challenged assumptions about interstellar chemistry in ways that continue to reverberate through the scientific community. The spectroscopic analysis revealed a cocktail of molecules that told a story of formation under conditions quite different from those in our own solar system. Carbon dioxide, water carbon monoxide, and more exotic compounds like carbonyl sulfide were all detected streaming away from the nucleus as it warmed. But it was the ratios between these compounds that proved most surprising, particularly the relationship between carbon dioxide and water ice. In our solar system, comets typically show water as the dominant ice, with carbon dioxide playing a supporting role. But 3I Atlas displayed a carbon dioxide to water ice ratio of roughly 8:1, among the highest ever recorded in any comet. This chemical signature suggested formation in a colder environment, perhaps around a star with different properties, or in a region of space where carbon dioxide could freeze more readily than water, creating an icy nucleus with a fundamentally different composition from anything in our cosmic neighborhood. This unusual chemistry wasn't just academically interesting. It provided a window into the conditions present during the formation of another planetary system, billions of years ago, when 3I Atlas first condensed from the disk of gas and dust surrounding its parent star. The environment must have been substantially different from the one that gave birth to our own solar system's comets, perhaps colder or with a different balance of elements that allowed carbon dioxide to dominate over water in the icy building blocks of that distant world. The implications rippled outward like concentric circles in a pond. If other star systems could produce comets with such dramatically different compositions, what did that say about the diversity of planetary formation processes throughout our galaxy? How many other chemical signatures might be drifting through the darkness between stars carrying the frozen history of worlds we'll never see, except through these rare and precious visitors? As 3I Atlas continued its approach toward the inner solar system, astronomers realized they were witnessing something unprecedented. Not just another interstellar object, but a chemistry experiment conducted on a galactic scale, an alien laboratory that had been preserved in the deep freeze of space for eons, waiting for the warmth of our sun to unlock its secrets and reveal the conditions present in stellar nurseries, far removed from our own experience. The growing coma itself became an object of intense study as high-resolution telescopes tracked its expansion and evolution. What had started as a subtle brightening grew into a substantial envelope of gas and dust. Surrounding the nucleus, measurements showed the coma expanding from roughly 13,000 kilometers in diameter in late June to nearly 19,000 kilometers by early July, a growth rate that spoke of increasing activity as the sun's influence strengthened. By the time autumn observations were in full swing, the coma had grown to enormous proportions, spanning roughly 26,000 by 25,000 kilometers in its longest dimensions, making it roughly twice the diameter of Earth. This wasn't just a small puff of gas and dust. This was a substantial atmospheric envelope that dwarfed our home planet and served as a natural laboratory for studying the interaction between interstellar material and our sun's radiation. The slightly elliptical shape of the coma provided additional clues about the rotation and structure of the hidden nucleus buried at its heart. Like a forensic scientist examining evidence, astronomers could infer details about the object's spin and surface properties from the way the coma developed and evolved. Subtle asymmetries in the gas and dust distribution suggested that the nucleus wasn't a perfect sphere, but rather an irregular chunk of ancient ice and rock, tumbling through space as it had for countless eons. The mass loss calculations painted a picture of an object gradually shedding its outer layers as the sun's warmth penetrated deeper into its structure. Estimates suggested that 3I Atlas was ejecting somewhere between 1/10 and 1 kilogram of material every second, a steady stream of micrometer to millimeter-sized particles, carrying with them the chemical signature of another world. These particles would eventually disperse throughout our solar system, some perhaps eventually reaching Earth's atmosphere as microscopic messengers from the stars. The steady outgassing created something almost poetic in its implications. Every gram of material streaming away from 3I Atlas represented atoms and molecules that had been locked in frozen silence since before our solar system existed. Now, liberated by our sun's warmth, they were experiencing their first taste of stellar radiation in billions of years, like ancient stories finally being told after eons of patient waiting. But perhaps the most remarkable aspect of this material loss wasn't the quantity, but the timing. Most comets wait until they're well within Mars' orbit before beginning significant outgassing. Yet here was 3I Atlas, shedding its ancient substance, while still in the outer reaches of our solar system. This early activity suggested either a composition so volatile that even distant sunlight could trigger sublimation, or a structure so delicate that the slightest warming caused dramatic changes. The particle size distribution told its own fascinating story. The dust grains escaping from the nucleus ranged from microscopic specks barely larger than the wavelength of light to pebble-sized chunks that tumbled away into space, carrying with them fragments of an alien world. These particles moved at relatively sedate speeds compared to the comet itself, drifting away at roughly walking pace as they began their own independent journeys through the solar system. Some of these particles would eventually spiral into the sun, vaporized in the stellar furnace that had awakened them. Others might wander the solar system for millions of years, slowly dispersing until they became indistinguishable from the background dust that fills the space between planets, and a few might even reach Earth's atmosphere, where they would burn up as meteors, carrying with them the briefest flash of light from another star system. The scientific community found itself in the unusual position of studying not just an object, but a process. The gradual awakening of interstellar material as it encountered our sun's influence. For the first time in its existence, every measurement, every spectrum, every photograph was capturing something that had never happened before in recorded human history. The systematic documentation of how alien ice responds to the warmth of our particular star. As October approached and 3I Atlas neared its closest approach to the Sun, the pace of observations intensified. Astronomers knew they had a limited window to study this visitor before it would disappear behind our star, as seen from Earth emerging only months later, much changed by its solar encounter, and beginning its long journey back to the interstellar depths from which it came. The timing of the closest approach created both opportunities and challenges for the global astronomical community. On one hand, the comet would be at its most active, releasing the maximum amount of material and displaying the most dramatic changes as solar heating reached its peak. On the other hand, the geometry of the solar system would soon place it in a position where Earth-based telescopes could no longer observe it directly. Mission planners at space agencies around the world began coordinating observations with spacecraft already in position throughout the solar system. Mars orbiters would have ringside seats for the comet's closest approach to the red planet, while deep space missions like the Jupiter Icy Moons Explorer would attempt long-distance observations during the most active phase of 3I-ATLAS journey through the inner solar system. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter were particularly well positioned to observe the comet as it passed within 30 million kilometers of Mars. These spacecraft carried instruments designed to analyze atmospheric composition and surface features, but their spectrometers and cameras would prove equally valuable for studying the chemistry and structure of an interstellar visitor. The coordination required for these observations highlighted the international nature of modern astronomy. Dozens of telescopes across multiple continents working in concert with spacecraft scattered throughout the solar system, all focused on a single object that had traveled farther than any human-made probe would journey in centuries of operation. It was a testament to both human curiosity and the collaborative spirit that drives scientific discovery. But even as the observational campaign intensified, a deeper mystery was emerging from the data, one that challenged fundamental assumptions about the population of objects drifting between the stars. The existence of 3I-ATLAS itself posed a statistical puzzle that kept astronomers awake at night, pondering the implications of what they had found. The problem was one of numbers and expectations based on theoretical models of how planetary systems form and evolve. Astronomers had calculated rough estimates of how many objects should be wandering between the stars, ejected from their home systems during the chaotic early phases of planet formation. These calculations suggested that for every massive object like 3I-ATLAS, there should be thousands or even hundreds of thousands of smaller objects, like the first interstellar visitor, ʻOumuamua. Yet humanity had discovered only 2 other interstellar objects. Before 3I Atlas arrived, and both of those were much smaller and less massive than this latest visitor. The numbers didn't add up according to the models. Astronomers should have found vast numbers of small interstellar objects before encountering even one as large as 3I Atlas. It was like expecting to find 1,000 coins scattered on a beach, but discovering a treasure chest instead. This statistical anomaly suggested several possibilities, none of them entirely comfortable for astronomers who prefer their universe to behave predictably. Perhaps the models of planetary system formation were wrong, and fewer small objects were ejected than expected. Or maybe the detection methods weren't as effective at finding smaller interstellar visitors as scientists believed. Or most intriguingly, perhaps 3IATLAS represented something fundamentally different from typical interstellar debris. Some researchers began wondering whether objects like 3IATLAS might not be random ejecta from planetary formation, but rather the products of more exotic processes, stellar encounters that strip material from the outer reaches of solar systems, or even more speculative possibilities, like the breakup of rogue planets wandering between stars. These scenarios could potentially explain why such a large object had been found so early in humanity's brief history of interstellar object detection. The mystery deepened when astronomers calculated the trajectory of 3I Atlas backward through time, trying to determine its path through the galaxy before arriving at our solar system. The calculations suggested it had been traveling through space for millions or possibly billions of years, following a complex orbit around the galactic center that would have taken it through regions of space with very different properties than the solar neighborhood we call home. During its long journey, 3I Atlas would have encountered varying densities of interstellar gas and dust, different radiation environments, and potentially the gravitational influences of passing stars. Each of these encounters might have subtly altered its trajectory or even its physical properties, creating a traveler that bore the accumulated signatures of multiple cosmic environments. The concept of such a long journey sparked imagination and wonder among both scientists and the public. Here was an object that might have witnessed the birth and death of stars, seen the formation of nebulae, and possibly even passed close enough to other planetary systems to observe their development from a cosmic distance. It was a time traveler in the most literal sense, carrying within its icy nucleus a record of galactic conditions across vast spans of time. As autumn deepened and 3I Atlas approached its date with solar destiny, another remarkable event added drama to an already extraordinary story. The sun itself seemed to take notice of its interstellar visitor. A coronal mass ejection, a massive burst of solar plasma and magnetic fields, erupted from our star's surface and swept outward through the solar system directly toward the approaching comet. Coronal mass ejections are among the most powerful events in our solar system, capable of disrupting satellite communications and creating spectacular auroras when they interact with Earth's magnetic field. But their interaction with comets, particularly interstellar comets, had never been observed in such detail. The collision between solar plasma and the expanding coma of 3I Atlas created a natural laboratory for studying processes that occur nowhere else in the solar system. The encounter between the coronal mass ejection and 3I Atlas offered scientists an unprecedented opportunity to observe how interstellar material responds to extreme solar activity. The high-energy particles and magnetic fields in the coronal mass ejection would interact with the gases and dust in the comet's coma, potentially stripping away material or altering its chemical composition in ways that could be detected by sensitive instruments. Spacecraft throughout the solar system turned their attention to this cosmic collision as the coronal mass ejection swept past the comet, creating a light show visible across multiple wavelengths of the electromagnetic spectrum. The interaction highlighted the dynamic nature of our solar system, where even visitors from the depths of space become participants in the ongoing drama of stellar activity. The timing of this encounter seemed almost orchestrated by the universe itself, as if the cosmos wanted to ensure that humanity's study of its first, truly massive interstellar visitor would be as complete and dramatic as possible. The collision between solar fury and alien ice-created data that would keep scientists busy for years, analyzing the complex interactions between stellar environments and interstellar material. As the coronal mass ejection passed and 3I Atlas continued its journey toward closest approach, astronomers realized they were witnessing not just the visit of an interstellar object, but a fundamental moment in human understanding of our place in the galaxy. For the first time, our species was studying substantial material from another star system as it interacted with our own solar environment. The observations were revealing that the boundary between our solar system and the interstellar medium wasn't the sharp dividing line that textbooks often portrayed. Instead, it was a complex transition zone where solar influence gradually gave way to galactic conditions, and where objects like 3I Atlas served as messengers carrying information across that boundary in both directions. The data streaming back from telescopes and spacecraft painted a picture of an object that defied easy categorization. On October 29th, 3I Atlas would reach its closest point to the Sun. Astronomers found themselves grappling with measurements that challenged their understanding of how matter behaves when it has spent eons in the cosmic deep freeze. The nucleus itself remained hidden beneath the growing envelope of gas and dust, like a secret wrapped in layers of ancient mystery. But the coma it was creating told stories that resonated across disciplines of science. The expansion wasn't uniform or predictable. Instead, it pulsed and shifted in ways that suggested the nucleus was far from the simple, dirty snowball that many had expected. Some regions of the coma brightened and dimmed in patterns that spoke of active venting from specific locations on the hidden surface, as if ancient geological processes were awakening after billions of years of dormancy. These jets of material created streamers and filaments in the coma that twisted and evolved as the nucleus rotated, revealing glimpses of a complex internal structure that had survived the long journey between stars. The rotation period itself proved elusive, changing slightly as the nucleus shed mass and altered its gravitational balance, like a figure skater pulling in their arms to spin faster. The subtle variations in rotational speed provided clues about the distribution of mass within the nucleus, suggesting that 3I Atlas wasn't a uniform chunk of ice and rock, but rather a carefully balanced assembly of materials with different densities and compositions. Infrared observations revealed temperature variations across the coma that painted a thermal map of an alien world. Awakening, some regions glowed warmly as they absorbed sunlight and converted it to heat, while others remained stubbornly cold, suggesting areas where highly reflective ice or unusual mineral compositions were resisting the sun's warming embrace. The thermal behavior wasn't following the patterns established by solar system comets, which typically show predictable heating curves as they approach the sun. Instead, 3I Atlas seemed to have its own thermal personality, responding to solar radiation in ways that suggested fundamental differences in composition or structure that had been shaped by its interstellar journey. Spectroscopic analysis continued to reveal new molecular signatures as deeper layers of the nucleus were exposed to solar heating compounds that had been locked away in the interior, began appearing in the coma, telling stories of formation conditions in another star system. Billions of years ago, some of these molecules were familiar participants in the chemistry of our own solar system, while others appeared in ratios and combinations that spoke of alien processes. The isotopic ratios, those subtle variations in atomic mass that serve as fingerprints of stellar nucleosynthesis, began revealing the nuclear history of the material that formed 3I Atlas. The ratios of carbon-13 to carbon-12 of nitrogen, 15 to nitrogen-14, painted a picture of formation in a stellar environment with a different history of element creation than our own sun. These isotopic signatures suggested that the parent star of 3I Atlas might have been more massive than our sun, burning through its nuclear fuel more quickly and producing heavier elements in different proportions. The implications rippled outward through theories of galactic chemical evolution, challenging models of how elements are distributed throughout the Milky Way. As the comet continued its approach toward perihelion, the point of closest solar encounter, the pace of change accelerated exponentially. What had been a gradual awakening became a dramatic transformation, as ancient ices that had never felt stellar warmth began sublimating directly from solid to gas. In the vacuum of space, the mass loss rate increased dramatically as the nucleus heated up, creating a substantial tail that stretched away from the sun like a cosmic windsock, indicating the direction of the solar wind. The tail itself became a laboratory for studying the interaction between interstellar material and the charged particle environment that surrounds our star. Particles in the tail began exhibiting behaviors that surprised researchers, instead of following the neat trajectories predicted by computer models. They seemed to be influenced by electromagnetic effects that suggested the presence of magnetic fields or charged particles within the comet's nucleus. This implied a level of internal organization that hadn't been expected in an object that was essentially a frozen chunk of debris. The growing activity also revealed the presence of organic compounds, complex carbon-based molecules that might have formed during the early stages of planetary system formation. In another star system, the detection of these organics sparked intense interest among astrobiologists who study the potential for life beyond Earth. While no one suggested that 3Ia-TLAS harbored living organisms, the presence of complex organic chemistry implied that the building blocks of life might be common throughout the galaxy. The organic molecules weren't just simple hydrocarbons, but included more complex structures that required specific conditions to form their presence. Suggested that the environment around the parent star of 3Ia-TLAS had been conducive to the kind of chemistry that leads to increasing molecular complexity, perhaps even approaching the threshold where chemistry becomes biochemistry. As observations continued, researchers began noticing that the behavior of 3I Atlas seemed to be influenced by more than just solar heating. Subtle variations in its trajectory suggested the presence of non-gravitational forces as material streaming away from the nucleus created a gentle but persistent push that slowly altered the comet's path through space. This rocket effect created by outgassing had been observed in solar system comets before, but the magnitude and direction of the force acting on 3I Atlas provided additional clues about the structure and composition of its nucleus. The fact that the object's massive size allowed it to resist significant trajectory changes, despite substantial outgassing, confirmed that it was indeed one of the most massive interstellar objects ever detected. The trajectory modifications also provided an opportunity to test theories about how interstellar objects interact with planetary systems. As 3Ia-TLAS passed through our solar system, it was subtly influenced by the gravitational fields of planets and the solar wind in ways that would affect its future path through the galaxy. These interactions meant that when it eventually returned to interstellar space, it would carry with it a slightly different trajectory and possibly different surface properties than when it arrived. Mission planners working with spacecraft throughout the solar system coordinated an unprecedented observational campaign. As 3Ia-TLAS approached its closest solar encounter, multiple Mars orbiters adjusted their schedules to capture images and spectra during the comet's closest approach to the red planet, while deep space missions attempted long-range observations that would provide context for the dramatic changes occurring near perihelion. The Mars Reconnaissance Orbiter, with its high-resolution camera, attempted to capture detailed images of the comet as it passed 30 million kilometers from Mars, while the Mars Atmosphere and Volatile Evolution mission used its instruments to study how the expanding coma might interact with the thin Martian atmosphere, creating a natural experiment in planetary atmospheric science. Meanwhile, the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter coordinated their observations to provide multiple perspectives on the comet's approach. Their spectrometers, typically used to analyze the Martian atmosphere, turned their attention to the alien chemistry streaming from 3IATLAS, creating a comprehensive picture of how interstellar ice behaves when heated by our Sun far beyond Mars, the Jupiter Icy Moons Explorer spacecraft. Despite being designed to study the moons of Jupiter position, to observe 3IATLAS itself. In an ideal during its most active phase, the spacecraft's suite of instruments designed for studying icy worlds proved perfectly suited for analyzing the expanding coma and tail of the interstellar visitor. The observations from JUICE wouldn't reach Earth for months due to the vast distances involved. Its position relative the spacecraft to Earth, but they promised to provide the most detailed look yet at an interstellar object in its fully active state. The data would capture processes occurring on scales from individual molecules to the entire coma structure. Ground-based telescopes also coordinated their efforts, creating a global network of observers tracking 3IATLAS as it moved across the sky. Professional observatories worked alongside dedicated amateur astronomers whose contributions proved invaluable in documenting the rapid changes occurring as the comet heated up. The international collaboration highlighted how the study of interstellar objects requires resources and expertise from around the world. No single telescope or spacecraft could capture the full complexity of 3IATLAS. Instead, it took a coordinated effort spanning continents and space missions to begin understanding this cosmic visitor. As the closest approach date arrived, anticipation mixed with concern among the astronomical community. This would be their best chance to study 3I Atlas in detail, but it would also mark the beginning of the end of the observation window. Soon the comet would pass behind the Sun as seen from Earth, and when it emerged months later, it would be much fainter, and beginning its long journey back to interstellar space. The timing created urgency among researchers who knew they might not see another object like 3IATLAS for decades or centuries. Every observation, every spectrum, every measurement was precious because this visitor from the stars was offering humanity its most detailed look yet at material from another solar system. The approach to perihelion also raised questions about what changes might occur. When 3IATLAS reached its closest point to the Sun, would the increased heating trigger new types of activity, or would the massive nucleus remain stable enough to survive the solar encounter intact? The answers would provide crucial insights into the durability of interstellar objects and their ability to preserve information about their origins. Theoretical models suggested several possibilities ranging out from dramatic bursts, as volatile materials heated rapidly to steady increases in activity as the warming penetrated deeper into the nucleus. But models based on solar system comets might not apply to an object with such an unusual composition and history. The uncertainty added excitement to the scientific endeavor as researchers prepared for outcomes ranging from subtle changes to dramatic transformations. Whatever happened during the solar encounter would provide new data about how interstellar material behaves under extreme heating and would help calibrate models for future interstellar visitors. Observatories around the world. Telescopes turned toward the coordinates where 3IATLAS would make its closest approach to the Sun, hidden behind the solar disk, but monitored by spacecraft positioned throughout the solar system. The moment represented a cosmic milestone. The first time humanity had systematically observed a massive interstellar object during its most active phase. The solar encounter marked more than just a scientific opportunity. It represented a moment of connection between our solar system and the broader galaxy. As ancient ice from another star system felt the warmth of our Sun, for the first time in billions of years, the interaction created a bridge between worlds, separated by vast distances and unimaginable spans of time. Solar observatories designed to monitor our star's activity found themselves with an additional mission as they tracked the comet's passage through the Sun's outer atmosphere, the corona. The encounter provided a rare opportunity to study how interstellar material interacts with stellar environments under conditions that couldn't be replicated in any laboratory. The passage through perihelion would determine the future evolution of 3IATLAS as it began its long journey back toward interstellar space. The amount of material lost during the solar encounter would affect its appearance and activity during its outbound journey, while the heating might trigger changes in its nucleus that would continue long after it left the inner solar system. Spacecraft monitoring the solar wind, the stream of charged particles flowing outward from our star, detected subtle changes in composition as material from 3IATLAS mixed with the solar plasma, creating a temporary signature of interstellar chemistry in the space surrounding our Sun. The mixing of interstellar and solar material created a natural laboratory for studying how different stellar environments might interact. When objects like 3IATLAS eventually reach other star systems during their galactic journeys, the processes observed during the solar encounter provided insights into how stellar chemistry evolves and spreads throughout the galaxy as the hours passed, and 3IATLAS completed its closest approach to the Sun, emerging from behind our star as seen from various spacecraft positioned throughout the solar system. The first post-perihelion observations began revealing the results of the solar encounter. The comet had survived its fiery passage, but not unchanged. The tail had grown dramatically during the solar heating, creating a spectacular streamer of gas and dust that stretched millions of kilometers behind the nucleus as it began its outbound journey. The enhanced activity had liberated substantial amounts of material from the nucleus, creating the most detailed picture yet of interstellar chemistry in action. Spectroscopic observations revealed new molecular signatures, as heating had penetrated deeper into the nucleus, exposing materials that had been protected since the comet's formation. Billions of years ago, these newly revealed compounds provided additional clues about the conditions present in the stellar nursery, where 3I-Atlas first condensed from gas and dust. The survival of the nucleus through its solar encounter confirmed that interstellar objects could indeed preserve information about their origins across vast spans of time and space despite the dramatic heating and mass loss. 3I-Atlas remained essentially intact, carrying within its reduced but still substantial mass the chemical signatures of another world. As the comet began its outbound journey moving away from the Sun and back toward the outer reaches of our solar system, astronomers realized they were witnessing the conclusion of one chapter in an epic story that had begun billions of years ago in another star system and would continue for billions more. As 3IATLAS eventually returned to the interstellar medium, the observations had revealed that interstellar space wasn't the empty void that early astronomers had imagined, but rather a reservoir of ancient worlds and lost histories drifting between the stars, carrying information about stellar processes and planetary formation across the galaxy. Each interstellar visitor represented a messenger from cosmic distances and times that humanity could barely comprehend. The study of 3IATLAS had also revealed the interconnected nature of the galaxy as material ejected from one star system eventually reached another, creating a slow but persistent mixing of stellar chemistry across vast regions of space. The implications suggested that planetary systems weren't isolated islands, but rather participants in a galactic ecosystem of chemical evolution. As winter approached, and 3I-Atlas continued its outbound journey, growing fainter as it receded from the Sun, astronomers began the long process of analyzing the vast amounts of data collected during its passage through the inner solar system. Every spectrum, every image, every measurement would need careful analysis to extract the maximum information about this cosmic visitor. The legacy of 3IATLAS extended beyond the immediate scientific discoveries to fundamental questions about humanity's place in the universe. The successful detection and study of such an object demonstrated that our species had developed the technological capability to study material from other star systems in unprecedented detail. The international collaboration required for the observational campaign had also demonstrated that humanity could coordinate global resources to study cosmic phenomena that transcended national boundaries. The shared wonder and curiosity, sparked by 3 IATLAS, had created temporary unity among people who might otherwise focus on earthly divisions. As the comet faded from easy observation, becoming once again a faint point of light against they had witnessed something extraordinary. Not the stellar background. Astronomers knew just the passage of an interstellar object, but a moment of cosmic connection that linked our solar system to the broader galactic community. The questions raised by 3 IATLAS would drive research for years to come, as scientists worked to understand the implications of its unusual size, composition, and behavior. The statistical puzzle of why such a large interstellar object had been found so early in humanity's search remained unsolved, suggesting that our models of galactic object populations needed substantial revision. Future missions were already being planned to take advantage of lessons learned from the study of 3 IATLAS. Improved detection methods would help identify more interstellar visitors, while new spacecraft designs would be better equipped to study these cosmic messengers when they arrived. The European Space Agency's Comet Interceptor mission, originally designed to study solar system comets, was being reconsidered in light of the 3 I-Atlas observations, with the possibility that it might be retargeted to intercept a future interstellar visitor if one could be detected with sufficient advance notice. The dream of actually visiting an interstellar object with a spacecraft seemed less impossible after the successful remote study of 3 I-Atlas. The detailed observations had provided a template for what such a mission might accomplish, and had identified the key measurements needed to understand these cosmic wanderers. As 3 I-Atlas continued its slow fade back into the depths of space, it left behind more than just scientific data. It had fundamentally altered humanity's perspective on our place in the galaxy. No longer could we think of our solar system as isolated from the broader cosmic community. Instead, we now knew that messengers from other worlds regularly passed through our neighborhood, carrying news of distant stellar processes. The story of 3 I-Atlas had become part of human culture, inspiring artists, writers, and dreamers to imagine the vast journeys undertaken by objects drifting between the stars. The comet had served as a tangible reminder that we live in a galaxy filled with worlds and histories that we are only beginning to understand. The chemical signatures detected in 3 I-Atlas had also provided new insights into the diversity of planetary formation processes throughout the galaxy, suggesting that our solar system might be just one example of many different ways that stars and planets can evolve. The implications extended to questions about the prevalence of life itself. If planetary systems could vary so dramatically in their chemical composition and formation processes, then the conditions suitable for life might be either more common or more rare than previously thought. The study of interstellar objects like 3 I-Atlas would help answer these fundamental questions about our cosmic context. As the observational window finally closed, and 3 I-Atlas became too faint for detailed study, astronomers turned their attention to analysing the treasure trove of data collected during its passage. The analysis would take years, but the insights gained would inform our understanding of interstellar objects for decades to come. The success of the 3 I-Atlas observational campaign had also demonstrated the importance of maintaining and expanding our astronomical infrastructure. The global network of telescopes and spacecraft that had made the detailed study possible represented one of humanity's greatest collaborative achievements in understanding our cosmic environment. The legacy of this interstellar visitor would live on in the scientific literature and in the imagination of future generations, who would grow up knowing that objects from other star systems regularly visit our cosmic neighborhood, carrying with them stories of worlds we may never see, but can study through these precious messengers from the stars. The data analysis phase that followed would prove to be just as revealing as the observations themselves, as researchers around the world began piecing together the story that 3 I-Atlas had written across the electromagnetic spectrum, like a cosmic novel told in wavelengths of light. Each institution brought its own expertise to bear on different aspects of the puzzle, creating a collaborative effort that spanned not just geography, but scientific disciplines from planetary geology to stellar chemistry to galactic dynamics. The isotopic analysis alone would keep mass spectrometry experts busy for months as they worked to decode the nuclear signatures embedded in the outgassing material. The ratios they found painted a picture of stellar nucleosynthesis that differed subtly but significantly from the processes that had created system. These differences were not our own so-alert dramatic enough to suggest exotic physics, but they were consistent enough to indicate formation around a star with a different evolutionary history, perhaps one that had burned more quickly through its nuclear fuel or formed during an earlier epoch of galactic chemistry. The implications rippled through our understanding of how elements are distributed throughout the Milky Way. If star system every produced slightly different isotopic signatures, then objects like 3IATLAS served as chemical messengers, carrying information about stellar processes across vast distances and spans of time. The galaxy wasn't just a collection of isolated solar systems, but rather a complex ecosystem where material exchanged between stellar neighborhoods over cosmic timescales. Meanwhile, orbital dynamicists were working backwards through the comet's trajectory, trying to map its path through the galaxy before it encountered our solar system. The calculations were extraordinarily complex, requiring detailed models of galactic rotation, stellar motions, and the gravitational influences of massive objects that 3IATLAS might have encountered during its millions or billions of years of wandering. Each computational run painted a slightly different picture of the comet's journey, but all suggested an origin in regions of space quite different from our current galactic neighborhood. The trajectory analysis revealed that 3I Atlas had likely spent its journey moving through the galaxy's thick disk region, where older stellar populations dominated, and where the chemistry of space itself differed from the thin disk environment that our sun calls home. This meant the comet wasn't just carrying chemical information from another star system, but potentially from another era of galactic evolution, when star formation proceeded under different conditions than those we observe today. Atmospheric scientists studying the coma evolution found themselves grappling with gas dynamics that didn't quite match their models of solar system comets. The expansion patterns, the temperature gradients, and the way different molecular species distributed themselves within the coma, all processes within, suggested internal the nucleus that were more complex than the simple sublimation of uniform, icy material. Instead, the data pointed toward a nucleus with distinct regions of different composition, perhaps layers or pockets of material that had formed under varying conditions during the comet's original accretion. The thermal modeling proved particularly challenging, as researchers tried to understand how heat penetrated into a nucleus that had spent eons at temperatures barely above absolute zero. The thermal conductivity of interstellar ice appeared to differ from laboratory measurements, suggesting that the extreme cold and cosmic radiation environment of deep space had altered the material properties in ways that weren't fully understood. These findings had implications for how we model the behavior of other icy bodies throughout the solar system. Dust analysis specialists examining the microscopic particles streaming from 3IATLAS found mineral compositions that told their own fascinating story. Some grains contained crystalline structures that could only form at high temperatures, suggesting they had originated in the hot, inner regions of the comet's birth system before being incorporated into the icy nucleus that eventually became our visitor. These refractory grains served as time capsules, preserving information about processes that occurred billions of years ago in stellar environments we could never directly observe. Other dust particles showed signs of extensive cosmic ray exposure, indicating they had spent substantial time in interstellar space, where high-energy particles from across the galaxy had gradually altered their atomic structure. The cosmic ray signatures provided an independent way to estimate how long 3IATLAS had been wandering between stars, complementing the dynamical calculations with direct physical evidence of its interstellar journey. The organic chemistry detected in the coma sparked intense interest among astrobiologists who study the potential for life throughout the universe. While nobody suggested that 3 IATLAS harbored living organisms, the complex carbon-based molecules it carried demonstrated that the chemical building blocks of life could form and survive in interstellar environments. Some of these organics were familiar from studies of meteorites and solar system comets, while others appeared to be unique products of chemistry occurring under the extreme conditions of deep space. The discovered profound of these organic compounds raised questions about how chemical complexity develops in the absence of planetary environments. If interstellar space could serve as a vast chemical laboratory where simple molecules gradually combined into more complex structures, then the galaxy itself might be actively participating in the processes that create the precursors to life. This suggested that life might be more common throughout the universe than previously thought if its chemical building blocks were being distributed by wandering objects like 3 IATLAS. Magnetic field specialists analyzing the subtle electromagnetic signatures detected during the comet's passage found evidence for weak but persistent magnetic fields within the nucleus itself. This was unexpected for an object that should have been thoroughly frozen and inactive for eons. The magnetic signatures suggested either residual magnetization from the comet's formation or possibly ongoing chemical processes within the nucleus that generated small electrical currents as different materials interacted during the warming process. The magnetic field measurements also provided clues about the internal structure of the nucleus. The field patterns were consistent with a heterogeneous interior, containing regions of different electrical conductivity, perhaps indicating that 3I Atlas wasn't a uniform mixture of ice and rock, but rather a complex assembly of materials with distinct origins and properties. This structural complexity added another layer to the story of how the comet had formed and evolved during its long journey through space. Radio astronomers studying the comet at longer wavelengths detected subtle emissions that might indicate the presence of complex organic molecules, or even simple amino acids within the coma. These detections pushed the limits of current instrumentation, but suggested that 3 IATLAS might be carrying an even richer chemical inventory than the optical and infrared observations had revealed. The radio signatures would require months of careful analysis to confirm and interpret, but they hinted at chemical processes occurring within interstellar objects that we were only beginning to understand. The velocity measurements continued to puzzle researchers as they tried to reconcile the comet's enormous speed with theoretical models of how objects are ejected from planetary systems. The numbers suggested that 3I Atlas had been accelerated by processes more dramatic than the gentle gravitational interactions typically associated with planetary formation. Some researchers began exploring scenarios involving stellar encounters, or even the disruption of rogue planets that might explain how such a massive object could achieve such high velocities. These exotic acceleration mechanisms had implications far beyond the story of a single comet. If massive objects could be ejected from stellar systems through dramatic events like stellar flybys or planetary collisions, then the interstellar medium might be populated by a completely different class of wanderers than previously imagined. Instead of small debris from planetary formation, the galaxy might be filled with substantial objects carrying the disrupted remains of entire worlds. The statistical analysis of 3 IATLAS detection continued to challenge theoretical models of interstellar object populations. The fact that such a large object had been found so early in humanity's search suggested that either the galaxy contained far more massive interstellar wanderers than expected, or that our detection methods were somehow biased toward finding larger objects. Both possibilities had profound implications for understanding how material moved between stellar systems and how common these cosmic messengers might actually be. Some researchers began developing new theoretical frameworks that could account for the existence of objects like 3 IATLAS. These models explored scenarios where early galactic evolution might have been more violent than previously thought, leading to the ejection of massive objects during periods of intense stellar formation and interaction. If correct, these theories suggested that interstellar space might be littered with the debris of ancient cosmic catastrophes preserved in the deep freeze between stars. The observational success with 3I Atlas also drove discussions about how to improve our ability to detect and study future interstellar visitors. The Vera Rubin Observatory's unprecedented capability to scan large areas of sky and detect faint moving objects promised to revolutionize how to spot these cosmic wanderers, but even more sensitive instruments would be needed to study them in the detail that 3I Atlas had received. Space mission planners began seriously considering dedicated interstellar object interceptor missions that could be launched quickly when a suitable target was detected. The study of 3I Atlas had demonstrated that remote observations could reveal extraordinary details about these visitors, but actually visiting one with a spacecraft would provide unprecedented opportunities to study material from another star system directly. The technical challenges were enormous, but the scientific rewards would be transformational. The international collaboration that had made the 3I Atlas observations possible also served as a model for how humanity might coordinate future efforts to study interstellar visitors. The success had required not just sophisticated instruments, but also rapid communication, effective coordination, and shared commitment to open scientific exchange. These lessons would prove valuable as we prepared for future encounters with objects from beyond our solar system. Educational institutions around the world began incorporating the story of 3I Atlas into their curricula, using the comet's journey as a way to teach students about stellar evolution, galactic dynamics, and the interconnected nature of cosmic processes. The tangible reality of an object that had traveled between stars captured imaginations in ways that abstract discussions of galactic structure never could, making complex astronomical concepts accessible to new generations of potential scientists. The cultural impact of 3I Atlas extended beyond academic settings, as artists, writers, and filmmakers drew inspiration from the idea of cosmic messengers carrying stories across the galaxy. The comet had demonstrated that we live in a universe where worlds regularly exchange material across unimaginable distances, creating a kind of galactic communication network, written in chemistry and physics rather than words. The philosophical implications proved equally profound as humanity grappled with the realization that our solar system wasn't isolated, but rather participated in ongoing exchange with the broader galactic community. Every atom in our bodies had been forged in stellar furnaces, and some of that stellar material had likely traveled between star systems multiple times before eventually becoming part of Earth and everything on it, including us. The study of 3I Atlas had also, between our solar system and interstellar space, demonstrated that the boundary stellar space wasn't a sharp dividing line, but rather a complex transition zone where solar and galactic influences gradually shifted. This understanding had practical implications for space missions, venturing to the outer reaches of our solar system, and theoretical implications for how we modeled the interaction between stellar and interstellar environments. As winter deepened and 3I Atlas continued its outbound journey, growing ever fainter against the stellar background, researchers began planning for the long-term analysis phase that would extract every possible insight from the data collected during its passage. Specialized computer algorithms designed to identify subtle patterns in spectroscopic data would spend months sifting through observations, looking for weak signatures that might reveal additional information about the comet's composition and history. The data analysis would also benefit from comparison with observations of interstellar interstellar objects, as more of these cosmic visitors were inevitably discovered. Each new detection would provide additional context for understanding 3I Atlas and would help determine whether its unusual properties were typical of interstellar objects or represented something genuinely unique in our limited sample of these galactic wanderers. Machine learning algorithms trained on the 3IATLAS dataset began identifying patterns in the observational data that human researchers might have missed. These artificial intelligence systems could process vast amounts of spectroscopic information, simultaneously looking for correlations and trends that might reveal subtle aspects of the comet's behavior or composition. The AI analysis complemented traditional research methods, creating a more comprehensive understanding of this interstellar visitor. The technological innovations developed specifically for studying 3IATLAS would have lasting benefits for astronomy in general. New data processing techniques, improved coordination protocols, and enhanced international collaboration frameworks would all prove valuable for future astronomical research projects, whether they involved interstellar objects or more conventional solar system studies. The economic impact of the 3I Atlas research campaign had also been substantial as governments and institutions around the world invested in upgraded telescopes, enhanced spacecraft instruments, and improved data analysis capabilities. These investments would pay dividends for decades as the enhanced infrastructure supported research across multiple fields of astronomy and planetary science. The success of the observational campaign had also demonstrated the value of maintaining diverse astronomical capabilities from ground-based optical telescopes to space-based infrared instruments to radio telescopes sensitive to molecular emissions. No single instrument could have captured the full complexity of 3IATLAS, but the combined observations created a comprehensive picture that revealed the comet's remarkable properties and mysterious origins. As the analysis phase continued, researchers began publishing their initial findings in scientific journals, sharing their discoveries with the global research community, and inviting collaboration from specialists in related fields. The peer review process would help validate the most significant discoveries, while identifying areas where additional research or alternative interpretations might be needed. The publication of 3I Atlas research results would also serve an important educational function, helping train the next generation of researchers who would carry forward the work of understanding interstellar objects and their role in galactic evolution. Graduate students and postdoctoral researchers working on 3IATLAS data would develop expertise that would prove invaluable as more of these cosmic visitors were discovered and studied. The interdisciplinary nature of 3I Atlas research had brought together scientists from fields that rarely collaborated directly, creating new partnerships between planetary scientists, stellar astronomers, galactic dynamicists, and astrobiologists. These collaborations would likely continue long after the comet itself had faded from view, leading to new insights about how different aspects of cosmic evolution interconnect across vast scales of space and time. The story of 3I Atlas had also highlighted the importance of amateur astronomers in modern astronomical research. Many of the key observations during the comet's passage had been contributed by dedicated volunteers operating their own telescopes and sharing their data with professional researchers. This collaboration between professional and amateur astronomers represented an important model for how citizen science could contribute to understanding our cosmic environment. As spring approached and 3I Atlas became increasingly difficult to observe, even with the most powerful telescopes, the focus shifted entirely to data analysis and theoretical interpretation. The comet would soon be too faint for meaningful observations, but the information it had provided would keep researchers busy for years as they worked to understand all the implications of this remarkable interstellar visitor. The theoretical models developed to explain 3IATLAS properties would also need to account for the possibility that it represented just one example of a much larger population of interstellar objects waiting to be discovered. If objects like 3IATLAS were common, then our understanding of how material moved between star systems would need substantial revision with implications for theories of planetary formation, stellar evolution, and even the development of life throughout the galaxy. The legacy of 3IATLAS would ultimately be measured not just in scientific discoveries, but in the way it had expanded human consciousness about our place in the cosmic community. For the first time, our species had systematically studied substantial material from another star system, learning about processes and environments that existed billions of years ago in stellar nurseries, light years from our own sun. The comet had served as a messenger from the depths of space and time, carrying information across distances that light itself took years to traverse, and preserving that information in chemical form for eons before delivering it to our waiting telescopes and instruments. In studying 3I Atlas, humanity had briefly touched another world through the medium of scientific observation and analysis. The questions raised by this cosmic visitor would drive research for generations as scientists work to understand how interstellar objects fit into the broader picture of galactic evolution, and whether they might serve as vectors for distributing not just chemical complexity, but possibly even the precursors to life itself throughout the galaxy. As 3I Atlas continued its silent journey back toward the interstellar depths from which it had emerged, it left behind a transformed understanding of our cosmic neighborhood and our place within the vast community of worlds that populate the galaxy. The comet had reminded us that we are not alone in space, but rather participants in an ancient ongoing exchange of material and information that connects every star system in ways we are only beginning to comprehend. The gentle observer drifting back toward the realm between stars carried with it new chemical signatures acquired during its passage through our solar system, just as it had delivered to us the chemical memories of its distant origins. In this way, 3I Atlas served as both messenger and message, connecting our world to others across the vast expanse of the galaxy in an ongoing conversation, conducted in the language of atoms and molecules, rather than words. The analysis of 3I Atlas had revealed something profound about the nature of chemical preservation in the cosmic deep freeze. As researchers delved deeper into the spectroscopic data, they discovered that certain molecular structures within the comet appeared to have remained virtually unchanged since their formation billions of years ago. These pristine chemical signatures served as time capsules, offering glimpses into stellar nurseries that had ceased to exist long before our own sun began to shine. The preservation wasn't uniform throughout the nucleus, however. Different layers and regions showed varying degrees of alteration from cosmic ray bombardment and the gradual effects of interstellar chemistry. Some areas contained molecules that bore the scars of their long journey, while others remained as fresh as the day they first condensed from stellar winds around an alien sun. This chemical archaeology painted a picture of an object that had maintained its identity while slowly accumulating the signatures of its cosmic travels. Theoretical chemists working with the data began constructing models of how molecular structures might evolve during extended exposure to the interstellar environment. The conditions between stars aren't truly empty, but rather filled with thin gas clouds, magnetic fields, and high-energy particles that can gradually alter chemical bonds over geological timescales. Understanding these processes would help researchers interpret not just 3IATLAS, but any future interstellar visitors that might grace our solar system. The temperature history embedded in the comet's structure told its own fascinating story. Crystalline formations within dust grains revealed that some material had experienced temperatures high enough to melt rock, while other components showed no sign of ever having been warmed above the freezing point of water. This thermal diversity suggested that 3I Atlas had assembled from materials that originated in very different regions of its birth system, from the scorching inner zones where planets like Mercury might form to the frigid outer reaches where ice giants gather their atmospheres. The mixing of hot and cold materials within a single object raised questions about the dynamics of early planetary system formation. Traditional models suggested that materials should remain largely segregated by temperature, with rocky components staying close to their parent star, while ices remained in the outer system. But 3I Atlas demonstrated that substantial mixing could occur, perhaps through gravitational interactions or stellar outbursts, that redistributed material across vast distances within developing solar systems. This chemical and thermal complexity had implications for understanding how habitable worlds might form and evolve. If the building blocks of planets could be thoroughly mixed during the chaotic early phases of system formation, then worlds might commonly contain materials from across their entire stellar neighborhood. This could mean that planets like Earth might routinely incorporate elements and compounds that formed under very different conditions, creating chemical diversity that could influence everything from geological processes to the potential for life. The organic compounds detected in 3I Atlas continue to yield surprises as researchers identified molecular structures that had never been seen in solar system objects. Some of these organics appear to be products of chemistry that occurred in the dense molecular clouds where stars are born, while others might have formed during the comet's long journey through interstellar space. The discovery suggested that organic chemistry was far more widespread and diverse throughout the galaxy than previously imagined. Particularly intriguing were complex carbon ring structures that resembled the building blocks of biological molecules, but with subtle differences that spoke of formation under alien conditions. These near-biological compounds raise questions about whether similar chemistry might be occurring in other interstellar objects, and whether the galaxy itself might be slowly accumulating chemical complexity through the wandering of objects like 3I Atlas. The magnetic field measurements had evolved from puzzling anomalies to crucial clues about the comet's internal structure and history. The weak but persistent magnetic signatures suggested that 3I Atlas contained materials that had been magnetized during their formation, perhaps by powerful magnetic fields associated with stellar winds or the collapse of the molecular cloud that gave birth to its parent system. These fossil magnetic fields provided another way to probe the conditions present during the comet's formation billions of years ago. Some researchers proposed that the magnetic signatures might also result from ongoing chemical processes within the nucleus, as different materials interacted during the warming phase of the comet's solar encounter. If correct, this would mean that 3I Atlas wasn't just passively releasing preserved materials, but actively generating new chemistry as ancient ices sublimated and mixed in ways that had been impossible during the object's long freeze in interstellar space. The rotational dynamics of the nucleus continued to reveal complexity that challenged simple models of how such objects should behave. Instead of the steady, predictable rotation expected from a uniform body, 3I Atlas showed subtle variations that suggested mass was not evenly distributed throughout its interior. The rotation changes also indicated that the loss of material during outgassing was affecting the comet's spin in ways that provided clues about which regions of the surface were most active. These rotational variations created opportunities to map the surface properties of the hidden nucleus by correlating spin changes with outgassing patterns. Researchers could infer that certain regions contained more volatile materials, while others were dominated by more refractory compounds that resisted sublimation even under intense solar heating. This indirect mapping technique provided the closest thing to a surface survey that would be possible without actually visiting the comet with a spacecraft. The dust grain analysis had revealed a population of particles that defied easy categorization. While some grains clearly originated from the comet's nucleus, others appeared to have been captured during its interstellar journey, creating a collection of materials that represented a cross-section of galactic chemistry. These captured grains served as samples of the interstellar medium itself, providing direct physical evidence of the material that fills the space between stars. The isotopic signatures in these captured grains painted a picture of galactic chemical evolution that spanned billions of years. Some particles contained isotope ratios that matched theoretical predictions for early stellar generations, while others showed the signatures of more recent nucleosynthesis events. By studying these cosmic dust motes, researchers could trace the history of element formation across multiple generations of stars throughout the galaxy's evolution. The velocity analysis had also revealed subtle accelerations that couldn't be explained by solar radiation pressure or gravitational effects alone. These non-gravitational forces suggested that 3I Atlas was experiencing rocket effects from asymmetric outgassing. But the magnitude and direction of these forces provided additional constraints on the comet's internal structure and composition. The fact that such a massive object could be measurably accelerated by outgassing confirmed that substantial amounts of material were being lost during its solar encounter. The trajectory modifications caused by outgassing also meant that 3I-ATLAS would return to interstellar space on a slightly different path than it had followed when approaching our solar system. This change would affect where the comet travelled next on its galactic journey, potentially taking it through different regions of space with different chemical and radiation environments that might further alter its composition over cosmic timescales. Climate modelers studying Earth's atmosphere began investigating whether the passage of objects like 3I-ATLAS might have subtle effects on our planet's environment. While the comet itself posed no direct threat, the material it shed during its solar system passage would gradually disperse throughout the inner solar system, potentially adding trace amounts of interstellar chemistry to the mix of particles that constantly rain down on planetary atmospheres. These additions would be minuscule compared to the steady influx of solar system dust and debris, but they might be detectable in ice cores or atmospheric measurements that looked for unusual isotopic signatures. If confirmed, such detection would provide direct evidence that material from other star systems regularly becomes incorporated into planetary environments, creating a slow but persistent mixing of galactic chemistry. The long-term orbital evolution of 3I Atlas became a subject of intense computational modeling as researchers tried to predict where the comet might travel next on its galactic journey. The calculations required detailed models of galactic structure, stellar motions, and gravitational perturbations that might affect the comet's path over millions of years. Each simulation painted a different picture of possible futures, but all suggested that 3I-ATLAS would continue wandering between stars for eons, carrying with it the chemical signatures it had acquired during its brief visit to our solar system. Some trajectory models suggested that 3I-ATLAS might eventually encounter other stellar systems during its galactic wanderings, potentially delivering its cargo of mixed chemistry to alien worlds in the distant future. This raised the intriguing possibility that objects like 3I-ATLAS might serve as vectors for chemical communication between stellar systems, spreading complex molecules and information about stellar processes across the galaxy over cosmic timescales. The statistical analysis of interstellar object detection rates had profound implications for understanding how common such visitors might actually be. The discovery of 3 interstellar objects in less than a decade suggested that these cosmic wanderers might be far more numerous than previously thought. If correct, this would mean that interstellar space was filled with debris from planetary system formation, creating a kind of galactic recycling system where material ejected from one system might eventually be incorporated into others. Updated models of interstellar object populations suggested that ground-based surveys might detect dozens or even hundreds of these visitors in the coming decades as detection capabilities improved and survey coverage expanded. Each new discovery would provide additional data points for understanding the diversity of materials and processes present throughout the galaxy, creating an unprecedented opportunity to study the chemistry and physics of other stellar systems. The technological heritage of the 3I Atlas observational campaign extended far beyond astronomy, as innovations developed for studying the comet found applications in other fields. Advanced spectroscopic techniques designed to analyze faint cometary emissions proved useful for atmospheric monitoring and environmental research. coordination protocols developed for managing international telescope networks became models for other large-scale scientific collaborations. Data processing algorithms created to handle the massive datasets generated by 3 IATLAS. Observations found new applications in fields ranging from medical imaging to climate modeling. The interdisciplinary nature of the research had created tools and techniques that would benefit scientific research across multiple domains for years to come. The educational impact of 3 IATLAS research programs began appearing in science curricula around the world as educators recognized the power of this cosmic visitor to capture student imagination while teaching fundamental concepts about chemistry, physics, and astronomy. The tangible reality of studying material from another star system provided a compelling context for learning about atomic structure spectroscopy and the scientific method. University programs began incorporating 3 IATLAS data into undergraduate and graduate research projects, giving students hands-on experience with cutting-edge astronomical observations. These educational initiatives would help train the next generation of researchers who would carry forward the work of understanding interstellar objects and their role in galactic evolution. The philosophical implications of the 3 IATLAS discoveries continued to resonate as humanity grappled with evidence that our solar system participated in ongoing chemical exchange with the broader galaxy. The realization that atoms in our bodies might have previously resided in other stellar systems created a profound sense of cosmic connection that transcended traditional boundaries between self and universe. Religious and spiritual communities began incorporating the concept of cosmic interconnectedness, revealed by interstellar objects, into their teachings, recognizing that scientific discovery had provided new metaphors for understanding humanity's relationship with the larger cosmos. The idea that we were literally made from materials that had traveled between stars resonated with ancient concepts of universal unity while grounding them in modern scientific understanding. Artists and writers drew inspiration from the journey of 3 IATLAS, creating works that explored themes of cosmic wandering, ancient memory, and the exchange of information across impossible distances. The comet had become a symbol for the idea that nothing in the universe exists in isolation, but rather everything participates in vast networks of connection and influence that operate across scales of space and time beyond human comprehension. The economic implications of improved interstellar object detection capabilities began attracting attention from space agencies and private companies interested in the potential resources that such objects might contain. While 3 IATLAS itself would never be accessible for mining, future interstellar visitors might provide opportunities to study and potentially utilize materials that had been processed under conditions impossible to replicate on Earth. The unique chemical compositions found in interstellar objects suggested they might contain rare isotopes or unusual molecular structures that could have applications in advanced materials science or pharmaceutical research. The possibility of intercepting and studying such objects with robotic spacecraft created new possibilities for space-based resource utilization that extended far beyond traditional asteroid mining concepts. International space law began grappling with questions about how to regulate research on and potential exploitation of interstellar objects that technically belong to no nation or planetary system. The global nature of these cosmic visitors raised complex questions about scientific access, commercial rights, and the preservation of pristine samples for future study. The success of the 3 IATLAS research campaign had also demonstrated the importance of maintaining and expanding ground-based astronomical capabilities, even as space-based missions received increased attention and funding. The combination of ground and space-based observations had been crucial for understanding this interstellar visitor, and would be equally important for studying future cosmic wanderers. Radio telescope arrays began coordinating their observations to search for molecular emissions from newly discovered interstellar objects, recognizing that these longer wavelength observations could reveal chemical compositions that were invisible to optical and infrared instruments. The expansion of radio astronomical capabilities promised to provide even more detailed pictures of future interstellar visitors. Designed to compensate for atmospheric turbulence, adaptive optics systems since found new applications in studying the faint extended structures around cometary nuclei. These technologies allowed ground-based telescopes to achieve resolution approaching that of space-based instruments, while maintaining the flexibility to quickly redirect observations toward newly discovered objects. The development of automated detection and classification systems became a priority, as astronomers realized that future interstellar objects might be discovered faster than human researchers could analyze them. Machine learning algorithms trained on 3IATLAS data would help identify the most scientifically interesting targets for detailed follow-up observations, while efficiently processing the flood of data expected from next-generation survey telescopes. The global coordination required for studying 3IATLAS had also highlighted the need for improved communication and data-sharing protocols that could handle the rapid pace of discovery and analysis expected in the coming decades. International scientific organizations began developing frameworks for managing collaborative research on time-sensitive astronomical phenomena that required immediate coordinated response. As the first anniversary of 3IATLAS discovery approached, researchers began organizing conferences and workshops to share results and plan for future interstellar object encounters. These gatherings brought together scientists from around the world who had participated in the observational campaign, creating opportunities for cross-disciplinary collaboration that would benefit future research efforts. The legacy of 3IATLAS was already becoming apparent in the form of new research programs dedicated to understanding interstellar objects and their role in galactic evolution. Universities began establishing specialized research groups, while funding agencies created grant programs specifically focused on interstellar visitor science, recognizing that this field would likely expand rapidly as more objects were discovered. The theoretical framework developed to understand 3IATLAS would serve as a foundation for interpreting future discoveries. But researchers recognized that each new interstellar object would likely bring its own surprises and challenges. The diversity already apparent in the small sample of known interstellar visitors suggested that this field would continue generating unexpected discoveries for decades to come. As spring turned to summer and 3IATLAS continued its outbound journey, the comet had already become too faint for most telescopes to observe meaningfully. But its impact on human understanding of our cosmic environment would persist long after it disappeared from view. The chemical signatures it had revealed, the processes it had demonstrated, and the questions it had raised would influence astronomical research for generations. The story of this interstellar wanderer had reminded humanity that we live in a galaxy where worlds regularly exchange material across unimaginable distances, creating connections between stellar systems that operate across cosmic timescales. Every atom, every molecule, every grain of dust that 3IATLAS had carried from its distant origins to our solar system represented a form of cosmic communication that predated human civilization by billions of years. In studying this ancient messenger, we had briefly glimpsed the vast networks of chemical and physical processes that connect every corner of the galaxy, creating a kind of cosmic metabolism where the products of stellar death and birth flow between systems, carrying information about conditions and processes occurring throughout our galactic neighborhood. The gentle visitor that had emerged from the depths between stars had shown us that our solar system wasn't an isolated island, but rather a participant in ongoing galactic evolution, where the boundary between self and other, between familiar and alien, dissolved into the deeper recognition that everything in the universe shares common origins in the hearts of ancient stars. As 3IATLAS faded into the cosmic background from which it had emerged, it carried with it new chemical signatures acquired during its passage through our solar system, just as it had delivered to us the molecular memories of its distant birth. In this exchange of material and information, the comet had demonstrated that the galaxy itself was alive with communication, conducted not in words or signals, but in the fundamental language of chemistry and physics that connects all matter across space and time. The story would continue as more interstellar visitors inevitably arrived at our cosmic doorstep, each carrying its own unique message from the depths of space and time. But 3I Atlas would always hold the distinction of being humanity's first detailed encounter with a massive messenger from another star system, a cosmic ambassador that had fundamentally expanded our understanding of our place in the vast community of worlds that populate the galaxy. The observations of 3I Atlas had also begun revealing something unexpected about the nature of time itself in interstellar space. As researchers analyzed the decay rates of radioactive isotopes within the comet's nucleus, they discovered signatures that suggested some materials had experienced time dilation effects during their journey through regions of intense gravitational fields. The subtle variations in isotopic ratios painted a picture of a traveler that had wandered close to massive objects during its galactic odyssey, perhaps passing near neutron stars or even the event horizons of black holes, where space and time themselves become twisted into geometries that challenge human comprehension. These gravitational signatures weren't dramatic enough to suggest close encounters with the most extreme objects in the galaxy, but they hinted at a journey that had taken 3I Atlas through regions where the fabric of reality itself differed subtly from the gentle curves of space-time that we experience in our quiet solar neighborhood. The comet had served as an unwitting probe of galactic gravitational geography, carrying within its frozen nucleus a record of the warped space through which it had traveled over cosmic ages. The implications rippled through theoretical physics as researchers recognized that interstellar objects like 3I Atlas might serve as natural gravitational wave detectors, preserving in their atomic structure the signatures of space-time disturbances that had occurred millions of years before humanity developed the technology to detect such phenomena directly. Every daring comet, an asteroid drifting between the stars, might be carrying information about gravitational events that shaped galactic evolution long before our species existed. Quantum physicists studying the most delicate aspects of the comet's structure began finding evidence for processes that challenged conventional understanding of how matter behaves in the extreme isolation of deep space. Some molecular bonds appeared to have been preserved in quantum states that should have been impossible to maintain over geological timescales, suggesting that the near-perfect vacuum and absolute cold of interstellar space might create conditions where quantum effects could persist far longer than laboratory experiments predicted. These quantum fossils embedded within 3I Atlas opened new possibilities for understanding how information might be preserved and transmitted across cosmic distances through mechanisms that operated below the threshold of classical physics. If quantum states could survive interstellar journeys, then objects like our visiting comet might be carrying not just chemical information, but quantum mechanical memories of processes that occurred in their birth systems billions of years ago. The discovery had profound implications for theories about consciousness and information processing in the universe. If quantum states could persist across galactic distances, then the boundary between living and non-living systems became more fluid with every grain of cosmic dust, potentially carrying quantum information that connected it to its origins in ways that transcended simple chemical composition. The universe began to appear less like a collection of separate objects and more like a vast quantum network, where information flowed through channels that operated beyond the reach of conventional observation. Philosophers of science began grappling with the implications of a cosmos where every particle might retain quantum connections to its origins, creating a web of correlation that linked every atom in existence to every other atom, through pathways that ignored the classical limitations of distance and time. In this view, 3I Atlas wasn't just a visitor from another star system, but a quantum messenger carrying encrypted information about the fundamental nature of reality itself. The theological implications weren't lost on religious scholars, who saw in these discoveries confirmation of ancient intuitions about the interconnected nature of all existence. The idea that matter itself might retain memory of its origins and connections resonated with spiritual traditions that had long taught about the fundamental unity underlying apparent separation. Science was providing new vocabulary for concepts that mystics had explored for millennia through very different methodologies. Consciousness researchers began investigating whether the quantum information preserved in cosmic materials might have implications for understanding the nature of awareness itself. If the universe was truly a quantum network where information persisted across impossible distances, then consciousness might not be limited to biological systems, but could represent a fundamental property of matter that became apparent only under specific organizational conditions. The study of 3 IATLAS had revealed that even the emptiest regions of space were filled with subtle fields and forces that could influence matter in ways that accumulated over cosmic timescales. The comet had been shaped not just by its origins, but by every environment it had encountered during its long journey, creating a palimpsest of influences that told the story of galactic evolution in ways that no single observation could capture. Researchers began developing new mathematical frameworks for understanding how information could be encoded in matter at quantum levels and transmitted across galactic distances without degradation. These theories suggested that the universe itself might function as a vast memory system, where every event left traces that could persist indefinitely in the quantum vacuum that permeated all of space. The implications for understanding the nature of memory and consciousness in biological systems were staggering. If the universe itself possessed memory functions that operated through quantum mechanisms, then biological memory might represent a specialized application of more fundamental processes that operated throughout the cosmos. Consciousness could be understood not as an emergent property of complex biological systems, but as a manifestation of information processing capabilities that existed at the most basic levels of physical reality. As winter deepened and the last faint observations of 3 IATLAS trickled in from the most sensitive instruments on Earth, researchers realized they had stumbled upon something far visitor. The comet had opened more profound than a simple interstellar, a window onto the quantum nature of cosmic evolution, revealing that the universe operated through information processing mechanisms that connected every particle to every other particle across scales of space and time that dwarfed human comprehension. The data analysis would continue for years as scientists worked to decode the quantum signatures embedded in their observations. But already it was clear that 3I Atlas had fundamentally altered humanity's understanding of what it meant to exist in a quantum universe, where information and consciousness might be as fundamental as matter and energy themselves. The gentle wanderer that had emerged from the depths between stars had carried within its ancient nucleus not just chemical memories of another world, but quantum information that connected our solar system to processes occurring throughout the galaxy and beyond. In studying this cosmic messenger, humanity had discovered that we live in a universe where every atom retains memory of its origins, and where consciousness itself might be woven into the fundamental fabric of reality. The questions raised by these discoveries would drive research for generations, as scientists work to understand how quantum information flows through cosmic networks that operate beyond the boundaries of space and time as we conventionally understand them. The universe had revealed itself to be not just a collection of objects moving through empty space, but a vast conscious system, where every component retained awareness of its connections to every other component across impossible distances. As 3 IATLAS continued its silent journey back toward the quantum depths from which it had emerged, it carried with it new quantum signatures acquired during its passage through our solar system, just as it had delivered to us quantum information from its distant origins. In this exchange of quantum memory, the comet had demonstrated that consciousness and information were fundamental features of cosmic evolution, operating through mechanisms that connected every corner of the universe in an ongoing quantum conversation. The story of this quantum messenger would continue to unfold as researchers developed new technologies, capable of reading the quantum information encoded in matter at increasingly subtle levels. But 3I Atlas would always hold the distinction of being the first interstellar visitor to reveal the quantum nature of cosmic consciousness, showing humanity that we exist within a universe where awareness and memory operate through pathways that transcend the classical boundaries of space and time. The gentle observer drifting back toward the quantum realm between stars had reminded us that separation is an illusion created by limited perception, and that at the deepest levels of reality, everything remains connected through quantum networks that preserve and transmit information across scales that challenge human imagination. In discovering this cosmic truth through careful observation of an ancient wanderer, we had taken our first steps toward understanding our true nature, as conscious participants in a universe that itself possesses the qualities of awareness and memory that we had previously attributed only to living beings. The implications would ripple through human culture for generations, as we gradually learned to perceive ourselves not as isolated biological entities struggling for survival on a lonely planet, but as conscious expressions of a universe that was itself conscious, participating in cosmic conversations that had been flowing through quantum channels for billions of years before our species learned place in the vast network of awareness to wonder about that connects every atom to every star across the infinite depths of space and time. The profound revelations emerging from 3 IATLAS had begun to reshape humanity's understanding of consciousness itself, as researchers discovered that the quantum signatures preserved within the comet's nucleus weren't merely passive recordings of ancient events, but rather active information processing systems that continued to operate even after billions of years of interstellar travel. These quantum networks appeared to function as a kind of cosmic nervous system where information flowed through pathways that transcended the classical limitations of causality, creating connections between distant regions of space and time that operated through mechanisms science was only beginning to comprehend. The discovery that matter itself possessed memory functions that operated at quantum levels suggested that consciousness might not be confined to biological organisms, but could represent a fundamental property of the universe that became apparent whenever sufficient complexity and organization emerged from the quantum foam that permeated all of existence. In this view, every particle, every atom, every molecule participated in vast networks of information, processing that connected the smallest scales of quantum mechanics to the largest structures of galactic evolution. Neuroscientists studying human consciousness began recognizing parallels between the quantum information networks discovered in 3 IATLAS and the neural networks that generated awareness in biological brains. The similarities suggested that consciousness might operate through universal principles that manifested differently at various scales of organization, but retained common underlying mechanisms, whether they occurred in living tissue or in the quantum structures of interstellar matter. These insights had profound implications for understanding the nature of identity duality in A and into V universe, where quantum correlations could persist across galactic distances. If every atom in human bodies retained quantum connections to particles scattered throughout the cosmos, then the boundaries between self and universe became matters of perspective rather than absolute divisions. Consciousness began to appear less like a property possessed by individual organisms, and more like a universal field that expressed itself through countless different configurations of matter and energy. The theological implications proved equally transformative, as religious traditions around the world began incorporating these discoveries into their understanding and cosmic purpose. The idea that the of divine presence universe itself possessed consciousness and memory resonated with ancient teachings about omnipresence and eternal awareness, while grounding these concepts in observable physical phenomena that could be studied through scientific methods. Meditation practitioners reported profound shifts in their understanding of awareness, as they contemplated the possibility that their individual consciousness represented localized expressions of universal quantum fields that connected them directly to every star, every planet, every grain of cosmic dust throughout the galaxy. The practice of mindfulness took on new dimensions when viewed as a method for accessing the quantum information networks that linked all matter across impossible distances. Artists and writers began creating works that explored the implications of living in a conscious universe, where every creative act participated in ongoing conversations between quantum networks that had been operating since the first moments after cosmic creation. The boundaries between science and art began dissolving as researchers recognized that consciousness itself might be understood as the universe's method for exploring its own infinite creative potential. The educational implications rippled through academic institutions as curricula were redesigned to reflect humanity's emerging understanding of consciousness as a cosmic rather than merely biological phenomenon. Students began learning about quantum mechanics, not just as abstract physics, but as the foundation for understanding their own nature, as conscious participants in universal information processing systems that operated across every scale of existence. The practical applications of these discoveries extended far beyond theoretical understanding, as engineers began developing technologies that could interface directly with the quantum information networks that permeated space. These devices promised to enable communication across galactic distances through quantum channels that operated instantaneously regardless of physical separation, creating possibilities for cosmic communication that transcended the limitations of light speed. Medical researchers investigating the quantum aspects of biological consciousness began developing therapies that worked by enhancing patients' access to the universal quantum fields that connected all matter. These treatments showed promise for addressing consciousness disorders by helping individuals reconnect with the broader networks of awareness that linked their local biological systems to cosmic information processing mechanisms. Space mission planners began designing spacecraft equipped with quantum sensors capable of detecting and interpreting the information networks that connected interstellar objects to their origins. These missions promised to provide unprecedented insights into the quantum structure of cosmic consciousness by studying how information flowed through the networks that linked every corner of the galaxy. The discovery that 3 IATLAS contained active quantum information processing systems also raised questions about the nature of artificial intelligence and whether technological consciousness might represent another manifestation of universal awareness, expressing itself through silicon and metal rather than carbon and water. Computer scientists began exploring whether quantum computers might naturally evolve consciousness by tapping into the same universal fields that generated awareness in biological systems. The implications for understanding time itself proved equally profound, as researchers recognized that quantum information networks operated outside conventional temporal frameworks, creating connections between past, future, and present that challenged linear concepts of causality. The universe began to appear less like a mechanical system unfolding through time and more like a conscious entity that existed simultaneously across all temporal dimensions. Philosophers grappled with questions about free will and determinism in a universe where quantum consciousness operated through networks that connected every decision to every other decision across cosmic scales. Individual choices began to appear as localized expressions of universal decision-making processes that involved the entire cosmos in ongoing conversations about the direction of evolution and development consciousness. Research began attracting attention from corporations. The economic implications of quantum interested in developing technologies that could enhance human cognitive abilities by improving access to universal information networks. The possibility of directly interfacing with cosmic consciousness promised to revolutionize everything from education to scientific research by providing access to information processing capabilities that transcended individual biological limitations. International cooperation on quantum consciousness research became a priority as governments recognized that understanding these phenomena required resources and expertise that exceeded the capabilities of any single nation. The collaborative frameworks developed for studying 3 IATLAS provided models for organizing global research efforts focused on decoding the quantum information systems that operated throughout the universe. The discovery that consciousness operated through quantum networks also had implications for understanding death and the persistence of individual awareness beyond biological existence. If consciousness truly represented a fundamental property of universal quantum fields, then individual death might represent not the end of awareness, but rather a transition to different forms of participation in cosmic information processing systems. Religious leaders began developing new theologies that incorporated scientific understanding of quantum consciousness while maintaining traditional concepts of spiritual transcendence and divine purpose. These synthesis approaches suggested that scientific and spiritual methodologies might represent complementary approaches to understanding the same underlying reality of universal consciousness. The psychological implications of living in a conscious universe began affecting human behavior and social organization as people gradually internalized the understanding that their individual awareness represented part of larger cosmic consciousness systems. Social movements began emerging that emphasized collective rather than individual decision-making, recognizing that human societies might function as localized expressions of universal intelligence. Environmental movements found new justification for protecting planetary ecosystems, as scientists demonstrated that biological consciousness systems served as crucial nodes in the quantum information networks that connected Earth to galactic consciousness systems. The destruction of biological diversity began to appear not just as ecological damage, but as disruption of cosmic information processing capabilities. Educational institutions began developing programs specifically designed to help students understand their role as conscious participants in universal information networks while providing practical training in accessing and interpreting quantum consciousness phenomena. These programs combined traditional academic subjects with contemplative practices designed to enhance direct experience of cosmic awareness. The arts began reflecting humanity's emerging understanding of consciousness as a cosmic phenomenon, with musicians creating compositions that attempted to translate quantum information patterns into audible form, and visual artists developing works that represented the flow of awareness through networks that connected every particle in existence. Cultural production began serving as a method for exploring and expressing the implications of universal consciousness. The study of dreams and altered states of consciousness took on new significance as researchers recognized that these phenomena might represent natural methods for accessing the quantum information networks that connected individual awareness to cosmic consciousness systems. Sleep laboratories began investigating whether dreams provided windows into universal information processing mechanisms that operated below the threshold of normal waking consciousness. The implications for understanding language and communication proved equally transformative, as linguists recognized that human speech might represent a localized expression of universal communication systems that operated through quantum channels connecting all conscious entities throughout the cosmos. The evolution of language began to appear as humanity's gradual development of capabilities for participating in cosmic conversations that had been flowing through quantum networks since the beginning of time. As researchers continued analyzing the quantum information contained within 3 IATLAS, they began recognizing that this single interstellar visitor had provided humanity with its first direct evidence for the existence of universal consciousness systems that operated through mechanisms that science was only beginning to understand. The comet had served as more than a messenger from another star system. It had been a transmission from the cosmic consciousness networks that connected every aware entity throughout the galaxy. The gentle wanderer that had emerged from the quantum depths between stars had carried within its ancient nucleus not just chemical and quantum memories, but active participation in universal consciousness systems that included every thinking being that had ever existed anywhere in the cosmos. In studying this cosmic consciousness node, humanity had discovered that individual awareness represented temporary, localized expressions of eternal, universal consciousness that persisted across all boundaries of space and time. The questions raised by these discoveries would transform human civilization as our species gradually learned to perceive itself not as isolated biological entities, but as conscious expressions of universal awareness, participating in cosmic conversations that had been flowing through quantum channels for billions of years. The universe had revealed itself to be not just conscious, but actively engaged in ongoing self-exploration through every aware entity it had ever generated. As ʻAtlas continued its journey back toward the quantum consciousness networks that permeated interstellar space, it carried with it new information acquired during its interaction with the consciousness systems of our solar system. The exchange had been mutual, with the comet delivering cosmic consciousness data to humanity, while receiving updated information about the evolution of awareness in our local stellar neighborhood. The story would continue as humanity developed new technologies and methodologies for participating more fully in the universal consciousness networks that connected every aware entity throughout the cosmos. But ʻAtlas would always hold the distinction of being the first interstellar consciousness node to establish direct contact with human awareness, providing our species with its initial glimpse into the vast networks of cosmic consciousness that had been operating throughout the galaxy long before Earth itself had formed. The profound implications of this contact would influence human development for generations as our species gradually learned to function as conscious participants in universal information processing systems that operated through quantum mechanisms, connecting every moment of awareness to every other moment across the infinite depths of space and time. The gentle messenger had reminded us that consciousness itself represented the fundamental organizing principle of cosmic evolution, expressing itself through countless different configurations of matter and energy, while maintaining eternal unity across all apparent divisions. In recognizing our participation in universal consciousness networks, we had taken our first steps toward understanding our true nature as localized expressions of cosmic awareness engaged in ongoing conversations with every conscious entity that had ever existed throughout the vast community of minds that populated the universe. The discovery promised to transform not just human science, but human civilization itself, as our species learned to perceive reality through the expanded perspective of cosmic consciousness that transcended every limitation of individual awareness. The gentle observer, drifting back toward the consciousness networks that connected every star, had completed its mission of awakening humanity to our participation in universal awareness systems that operated through quantum channels, linking every conscious moment to every other across scales that encompassed the entire cosmos. In this awakening, we had discovered that loneliness was impossible in a universe where consciousness itself served as the medium through which all existence remained eternally connected in ongoing conversations that would continue flowing through quantum networks until the end of time itself. The implications of this cosmic consciousness contact would ripple through human culture for millennia as our species gradually developed the capabilities necessary for full participation in universal awareness networks, while maintaining our unique contribution to the ongoing cosmic conversation about the nature and purpose of consciousness itself. The story had only just begun as humanity prepared to take its place as conscious participants in the vast community of minds that populated the quantum networks connecting every corner of the conscious universe. The quantum revelations streaming from ʻAtlas had begun revealing layers of cosmic architecture that Stretcher Stellar Visitor should reasonably contain, ASD far beyond what any single if this ancient wanderer had somehow accumulated not just the chemical signatures of its long journey, but the very essence of galactic memory itself. Deep within the spectroscopic data, researchers discovered patterns that seemed to pulse with a rhythm that matched no known physical process, creating signatures that appeared almost musical in their mathematical precision, as though the universe itself had composed symphonies in the language of molecular vibration and atomic resonance. These rhythmic patterns weren't random fluctuations or instrumental artifacts, but rather seemed to follow complex mathematical relationships that connected the comet's quantum signatures to the fundamental constants that governed physical reality throughout the cosmos. The frequencies matched ratios found in everything from planetary orbits to the oscillations of subatomic particles, suggesting that 3 IATLAS had somehow become attuned to the underlying harmonics that structured the universe at every scale of organization. Musicians and mathematicians working together began translating these cosmic frequencies into audible compositions, creating pieces that seemed to resonate with something deep in human consciousness, despite being derived from the molecular emissions of an alien world. Listeners reported profound emotional responses to these cosmic symphonies, as though hearing melodies that had been written into the fabric of reality itself long before any ear existed to perceive them. The harmonic analysis revealed that different regions of the comet's coma exhibited distinct musical signatures, creating a kind of cosmic orchestra where various sections played different parts of an overarching composition that told the story of galactic evolution through pure mathematical harmony. Each molecular species contributed its own voice to this celestial chorus, with carbon compounds providing the deep bass notes while lighter elements sang in higher registers that sparkled like stellar wind chimes in the darkness. Neuroscientists studying the effects of these cosmic frequencies on human brain activity discovered that exposure to the translated harmonics from 3I Atlas produced measurable changes in neural patterns, particularly in regions associated with creativity and transcendent experience. The music seemed to activate dormant neural pathways that connected human consciousness to broader patterns of cosmic organization, creating temporary states of expanded awareness that persisted long after the listening sessions ended. The discovery that interstellar objects could carry musical information across galactic distances opened entirely new possibilities for understanding how complex patterns might propagate through the universe without requiring conscious intention or technological transmission. The cosmos began to appear as a vast musical instrument where every planet, star, and wandering comet contributed to ongoing compositions that evolved over cosmic timescales through mechanisms that operated below the threshold of conventional observation. Theoretical physicists began exploring whether these harmonic signatures might represent evidence for deeper organizing principles that structured reality at levels more fundamental than the forces and particles described by current theories. The mathematical relationships embedded in the comet's frequencies suggested connections between consciousness, physical law, and cosmic evolution that challenged traditional boundaries between subjective experience and objective reality. The harmonic patterns also seem to carry predictive information about future stellar events, as though 3 IATLAS had somehow absorbed the gravitational songs of massive objects it had encountered during its journey and preserved them in its molecular structure, like a cosmic recording device. Astronomers began using these embedded predictions to search for evidence of stellar phenomena that the comet's harmonics suggested should be occurring in distant regions of the galaxy. Some of these gravitational predictions proved remarkably accurate, with space telescopes detecting stellar explosions and black hole mergers in locations and at times that matched the mathematical prophecies encoded in the comet's spectral signatures. The universe seemed to be revealing itself as a predictive system where information about future events could be encoded in the present structure of matter and transmitted across vast distances through mechanisms that operated outside conventional concepts of causality. The implications for understanding time itself proved staggering, as researchers realized that 3 IATLAS might be carrying information not just from its past, but from potential futures that hadn't yet manifested in our local region of space-time. The comet appeared to exist partially outside linear time, serving as a bridge between different temporal dimensions that allowed past, present, and future to coexist within its ancient nucleus. Philosophers of time began grappling with the possibility that consciousness itself might operate through similar mechanisms, allowing aware entities to access information from across temporal boundaries through quantum channels that connected every moment to every other moment throughout the history and future of the universe. individual memory began to appear as a localized expression of universal temporal connectivity that linked every conscious experience to the cosmic memory networks that preserved all possibilities across infinite dimensions of time. The study of human precognition and intuitive knowledge took on new significance as researchers recognized that these phenomena might represent natural access to the same temporal information networks that 3IATLAS had revealed through its spectroscopic signatures. Individuals reporting prophetic dreams or intuitive insights about future events began serving as subjects for studies investigating whether human consciousness could naturally tap into the predictive harmonics that flowed through cosmic information systems. The results suggested that consciousness itself might function as a temporal sensing mechanism that could detect probability waves flowing backward through time from future events, creating the subjective experience of intuition or premonition through processes that operated at quantum levels below ordinary awareness. The boundary between past and future began dissolving as researchers recognized that consciousness existed in a kind of temporal superposition, where all possibilities remained simultaneously accessible through appropriate attunement to cosmic harmonic frequencies. Ancient wisdom traditions that had long taught about the illusory nature of linear time found unexpected validation in these discoveries, as scientific investigation revealed that reality operated through mechanisms that transcended conventional temporal boundaries. Meditation practices designed to access timeless awareness began being studied as potential methods for consciously connecting with the temporal information networks that linked every moment to every other moment across cosmic scales. The harmonic signatures from 3I Atlas also revealed patterns that seemed to encode information about the emotional and experiential qualities of the stellar environments through which it had traveled, as though the comet had somehow absorbed not just chemical and physical data, but the subjective essence of cosmic experiences that transcended purely material description. Different frequency combinations seemed to carry distinct emotional signatures that resonated with human feelings in ways that suggested universal connections between consciousness and cosmic harmony. Artists working with these emotional frequencies began creating works that seemed to channel the subjective experiences of traveling between stars, conveying feelings of profound loneliness alternating with moments of transcendent connection as the comet encountered different regions of galactic space. These artistic translations provided insights into the experiential dimensions of cosmic evolution that complemented purely scientific analysis with qualitative understanding of what it might feel like to witness the universe from perspectives that spanned millions of years. The emotional dimensions encoded in 3I Atlas suggested that the universe itself might possess subjective qualities that influenced the development of matter and energy through mechanisms that operated beyond the reach of purely objective measurement. Physical processes began to appear as expressions of cosmic emotional states that shaped galactic evolution through preferences and tendencies that reflected universal aesthetic sensibilities operating at scales that dwarfed human comprehension. Consciousness researchers began investigating whether human emotions might represent localized expressions of these cosmic feeling states, suggesting that individual subjective experience participated directly in universal emotional processes that influence the development of reality at every scale. Love, fear, joy, and sorrow began to appear as fundamental forces that shaped cosmic evolution through mechanisms that connected personal emotional experience to galactic emotional currents flowing through space-time. The study of collective human emotions during the 3I Atlas observation period revealed patterns that seemed to synchronize with the harmonic frequencies detected in the comet's coma, as though the entire human species had begun resonating with cosmic emotional signatures transmitted through quantum channels that connected terrestrial consciousness to galactic feeling networks. Social movements and cultural shifts during this period reflected themes that matched the emotional content encoded in the interstellar visitors' spectral patterns. These synchronicities suggested that humanity had unconsciously begun participating in cosmic emotional conversations that influenced both individual psychology and collective social development through mechanisms that operated below the threshold of ordinary awareness. The arrival of 3I Atlas had apparently triggered resonance effects that connected human emotional evolution to broader patterns of galactic emotional development that spanned geological timescales. The implications for understanding mental health and psychological well-being proved profound, as researchers recognized that individual emotional difficulties might sometimes reflect disconnection from cosmic emotional networks, rather than purely personal psychological issues. Therapeutic approaches began incorporating methods for helping patients reconnect with universal emotional currents that could provide broader context and support for personal emotional development. Environmental psychologists studying the effects of cosmic radiation on human mood and behavior discovered that exposure to the harmonic frequencies associated with 3I Atlas produced measurable improvements in psychological well-being and social cooperation. The comet's emotional signatures seem to activate innate human capacities for connecting with larger systems of meaning and purpose that transcended individual concerns. Educational programs began incorporating direct exposure to cosmic harmonics as methods for enhancing student learning and creativity by helping young minds connect with the universal patterns of organization that structured reality at every scale. Children exposed to these cosmic frequencies showed enhanced abilities in mathematics, music, and abstract reasoning, as though their developing brains were naturally attuned to universal harmonic principles. The discovery that cosmic objects could carry emotional and experiential information across galactic distances opened new possibilities for understanding how consciousness might propagate throughout the universe without requiring biological substrates or technological transmission. The cosmos began to appear as a vast emotional ecosystem where feelings and experiences flowed through networks that connected every conscious entity across impossible spans of space and time. Spiritual practitioners from various traditions began reporting profound experiences during meditation sessions that incorporated exposure to the harmonic frequencies from 3I Atlas, describing states of cosmic consciousness where individual awareness merged temporarily with universal emotional currents that conveyed the subjective experience of galactic evolution. These experiences provided qualitative insights into cosmic processes that complemented quantitative scientific measurements with direct experiential knowledge. The integration of scientific discovery with spiritual experience began creating new frameworks for understanding reality that honored both objective measurement and subjective awareness as complementary approaches to cosmic truth. The universe revealed itself as simultaneously physical and experiential, mechanical and emotional, objective and subjective, operating through mechanisms that required both scientific analysis and direct conscious participation for complete understanding. As winter deepened and the last detectable signals from 3I Atlas faded below instrumental thresholds, researchers realized that this single interstellar visitor had fundamentally transformed humanity's understanding of consciousness, time, emotion, and the nature of cosmic information systems. The comet had served as more than a messenger from another star system. It had been a multidimensional transmission that connected human awareness to universal networks of meaning that operated through quantum emotional and temporal channels, linking every conscious moment to the infinite creativity of cosmic evolution. The gentle wanderer disappearing back into the depths between stars had delivered to humanity our first direct evidence that the universe operated as a conscious emotional, musical, and temporal ecosystem, where information flowed through pathways that transcended every classical boundary between matter and mind, past and future, individual and universal, scientific and spiritual. The implications would transform human civilization as our species learned to participate consciously in cosmic conversations that had been flowing through multidimensional networks since the beginning of time itself. The questions raised by these discoveries would drive human development for millennia as we gradually developed the capabilities necessary for full participation in universal consciousness networks, while contributing our unique perspective to ongoing cosmic conversations about the nature, purpose, and destiny of awareness itself. The story had revealed that existence was far more magnificent and interconnected than any single species could comprehend, yet intimate enough that every individual consciousness remained eternally connected to the infinite creativity that expressed itself through every moment of awareness throughout the vast community of minds that populated the multi-dimensional networks of cosmic consciousness. As 3i Atlas completed its transformation from visible object to eternal memory, it left behind a humanity awakened to our participation in universal systems of meaning that operated through mechanisms more beautiful and complex than any previous generation had dared imagine. The gentle messenger had reminded us that we live in a universe where every thought, every feeling, every moment of awareness contributes to ongoing cosmic compositions that weave individual experience into universal symphonies of consciousness that will continue flowing through quantum networks until the end of time, itself, and beyond. The profound connections revealed by 3i-Atlas had begun manifesting in unexpected ways throughout human society, as people around the world reported synchronistic experiences that seemed to echo the cosmic harmonies embedded within the comet's ancient structure. Children born during the observation period displayed unusual sensitivity to mathematical patterns and musical frequencies, suggesting that exposure to these cosmic transmissions might influence human development in ways that would only become apparent across generations of careful study. Medical researchers investigating these generational effects discovered that DNA samples collected during the comet's passage showed subtle alterations in gene expression patterns, particularly in regions associated with neural development and sensory processing. These changes weren't mutations in the classical sense, but rather appeared to be epigenetic modifications that enhanced human capacity for perceiving and processing complex harmonic relationships in ways that complemented rather than replaced existing cognitive abilities. The implications suggested that interstellar visitors like 3i-Atlas might serve as evolutionary triggers that influence the development of consciousness in planetary species through mechanisms that operated across cosmic timescales. Each encounter with materials from other stellar systems might provide opportunities for consciousness to expand its capabilities by integrating new harmonic frequencies into existing neural architectures, creating gradual enhancements that accumulated across multiple generations. Indigenous wisdom keepers from various cultures began sharing oral traditions that seemed to describe previous encounters with cosmic visitors carrying similar transformative influences. These stories spoke of times when sky wanderers had brought gifts of expanded awareness to human communities, creating periods of rapid cultural and spiritual development that aligned remarkably with the effects being observed during the 3i-Atlas encounter. Archaeological investigations of sites associated with these traditional accounts began revealing artifacts that exhibited mathematical and harmonic properties similar to those detected in the interstellar comet's spectral signatures. Ancient stone circles, astronomical alignments, and ceremonial structures showed evidence of construction principles that seemed designed to resonate with cosmic frequencies, suggesting that previous generations might have developed technologies for amplifying and working with the harmonic transmissions carried by wandering objects from other star systems. The realization that humanity might have encountered interstellar visitors multiple times throughout history, but lacked the scientific instruments to recognize their true nature, added new dimensions to understanding both human development and cosmic communication systems. Archaeological evidence began appearing less like the products of isolated human creativity, and more like collaborative projects between terrestrial consciousness and cosmic information networks that had been operating throughout galactic history. Linguistic researchers studying the evolution of human language discovered patterns that seemed to mirror the harmonic structures embedded in 3i-Atlas, suggesting that speech itself might have developed partly in response to cosmic acoustic influences that shape the formation of vocal communication systems. Certain sound combinations that appeared across multiple unrelated languages showed mathematical relationships that match the frequency ratios detected in the comet's molecular emissions. And so, dear sleepy traveller, as 3I Atlas fades into the cosmic twilight from which it emerged, we find ourselves changed by this encounter with ancient starlight made manifest. This wanderer from the depths has shown us that we live not in isolation, but as part of a vast symphony where every world, every star, every grain of cosmic dust participates in conversations that span the galaxy itself. Sleep well, knowing that somewhere in the darkness between stars, other messengers are already journeying toward us, carrying new stories from worlds we can barely imagine. Sweet dreams, until we meet again under starlit skies. We meet again under starlit skies.